Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Today we are recording the rest of the topic of discrete probability distribution, and if we revise our outline, we'll note that we have covered the first four probability distribution, and we still need to cover the hypergeometric distribution and the Poisson probability distribution. Before we go to explain the hypergeometric distribution, I still have an example that I did not discuss with you yet, which is example number 9 under the negative binomial probability distribution. This example, in fact, have many ideas I need to discuss with you. So move back to slide number 20. In this example, we have a probability of a child exposed to a certain disease to catch is 0.2. The first question is, what is the probability that among 12 children exposed to the disease, only 3 will catch the disease? As we used for each probability distribution, we all the time define two components or two indicators: the random process or the experiment and the random variable. According to the information we have in this item, we have been told that we selected 12 distribution, a sample of 12 children. And each children may be exposed to the disease or not. So we have a limited number of trials, and each trial have two outcomes: either the child with the disease or without the disease. And he asked me in the question to compute the probability that 3 children have the disease. So I'm interested in having the disease, so this will be the success for me. Regard to the experiment, as we can see here, is selecting a children, and as long as it doesn't mention anything about the type of selection, we'll consider the selection is done with replacement. So if we try to revise all the information that we introduced in the previous probability distribution, we can consider this experiment belongs to the binomial distribution. So move to our board here. We can define the n, which is the number of the whole trials, equal 12, and we can define a random variable y as number of the children with the disease among those 12. So the probability of y equal a certain value will be computed as 12, which is y. The probability of success to the power y, and the probability of failure to the power the difference, 12 minus y, and y takes the value from 0, 1, 2 up to 12. So within the limited number or the finite number 12, we can have none of the children have the disease, maybe 1 children have the disease, 2 up to 12. Number A, interested of having 3 children with the disease. So we'll substitute in this. Formula with y equal 1. With y equal 3. So we need to find the probability that y equal to 3, which is given by 12 to 3 0.2 to the power 3 and 0.8 to the power 9. The final answer is presented in the slides. Now move to number B. Number B, what is the probability that the 12th child exposed to the disease will be the first to catch it? Again, try to revise all the information that I gave to you through the previous 4 distribution. Now we are interested to the first child catch the disease, which is the first success to me. What is the experiment that interested in the number of trials be observed until the first success? Of course, this will be the geometric experiment. So in number B, we'll define here a new random variable y will denote to the number of children will be observed until having the first child with the disease. So the first child with the disease for me is considered the first success. According to what we have learned, y in this case will belong or follows the geometric distribution with, we define the geometric distribution with only one parameter, which is the probability of success. We can say G with probability of success B equal 0.2. Fine? So all we need now is to find the probability that y equal 12. So we need to revise the formula. We need to return back to the formula of the probability mass function of the geometric distribution, which is given by the probability of y equal y is represented by 1 minus b, which can be substituted here by 0.8 to the power y minus 1 times the probability of success. According to the statement of question B, we are interested to find the probability that y equals 12. So we'll substitute in this formula by y equal to 12. So we have 11 failure and then, or 11 children with no disease, and the last one will be, which is number 12, will be with the disease. Again, the final answer is given in the slides. Now move to answering the last one. Number C, what is the probability that the 12th child exposed to the disease will be the third to catch it? Again, the success for me is having the disease. The child is getting the disease. And here in number C, we are interested to have 3 successes. And this, according to what we have learned from the previous probability distribution, this will be this will belong to the negative binomial probability distribution. So in number C, We'll define a number, the random variable is a number of children observed until having R, which is here 3, with the disease. Again, with the disease is the success for me. So we need to have 3 successes. To find the probability that y equal a certain value y, we need to substitute in the formula of the negative binomial distribution. I'm sorry, we still need to define the probability distribution of y, or we can say, we have to say that y will belong to the negative binomial with 2 parameters, r equal 3 and probability of success equal 0.2. Fine? We need to remember the probability mass function of the negative binomial distribution, which is y minus 1. We choose r minus 1, which is 2 here, times the probability of success to the power r times the probability of failure to the power the difference between the number y, the value of the random variable, and the number of successes r, which is y minus r. Y minus r. So to find the probability that y equal 12 here, we'll just substitute in this formula. طبعا we have to add the domain of the random variable, y equal to 3, 4, 5, and here we have y have infinite but countable values. So the probability of y equal 12 will substitute in this formula by y equal 12. So this will compute it as 11, which is 2 times 0.2 to the power 3. I'm sorry, let's move a bit down here. This will be 11, which is 2 times the probability of success all to the power 3 times 0.8, the probability of failure to the power y minus r, which is 12 minus 3, which is 9. And the final answer is added to this slide. I hope this is very clear. It is very important exercise. Now move to explaining the next kind of probability distribution, which is the hypergeometric probability distribution. The first property that we have under this kind of distribution, that we assume that we have a population contains a finite number n of elements, and those number of elements n, or capital N, possess one of 2 characteristics, f and f complement. We'll consider the characteristic f as the success, so the f complement will denote to the failure. The next property that we have, or we assume that we have our element belongs to the characteristic f, so the remaining number that belongs to the other characteristic will be n capital minus r. We'll define, as we already used in the previous probability distribution, we all the time define 2 components, the experiment or the random process and the random variable. Here we are interested in selecting a sample of size n, small n, to differentiate between small n and capital N. So small n will present the sample that we are selecting from the population, and the selection will be assumed to be done without replacement. So this is very important concern here, which is completely different than the binomial distribution. because the selection is done without replacement, so the successive trials will not be independent. I think we can move to the board to summarize all the information that we have until now. Again, we have a population of size n, and this population is divided into two parts. A part that belongs to the F characteristic and another part that belongs to the F complement. Again, the F will represent the success and the F complement will represent the failure. We assume also that in the population, the number of successes assumed to be R, and hence the number of failure will be considered as N capital minus R. So R, again, is the number of successes. While N capital minus R will be considered as the number of failures. Now we are interested in selecting, or the experiment is selecting a sample of size n or small n from the population of size capital N. So if we try to revise the counting technique that we introduced in the first lecture, the introduction to probability, so it is very easy to compute the number of elements in the sample space. This will consider as the number of possible samples of size n. So we're just choosing n or small n from capital N. This can be done by how many number of ways? It will be n capital choose small n, which is a combination rule. Now move to our presentation to next define the random variable. The random variable here, we define x to denote the number of elements with characteristic f. So we can say that x is the number of successes, as long as we are interested that n is the elements that belongs to the first characteristic, which is a success. So x will be the number of successes in the sample, right? So this is very similar to the binomial distribution, except for that the X selection is done without replacement. Okay, so all conditions of the binomial distribution will not satisfying here, so the binomial distribution is not appropriate for this kind of experiment. So the random variable x could have possible values of 0, 1, 2, up to n. So we can have a random variable that the number of successes equals 0. We don't select any items from they are element, right? Or we can choose one element, or we can choose an element, or we can choose all the sample space from the part of the successive or the part of belongs to the characteristic f, which is a success. So the n successes. A kind of this exercise, if we try to develop the probability distribution here, we can say the probability that x equal to a certain number x will be, it's a kind of an ordinary probability problem. Okay, we divide the total number that satisfy the event X divided by the total number of the sample space. So the denominator here is known to be n choose n. We already know that. But the numerator will be the possible number of samples of X and n minus X. We have n successes and n minus X failure, right? So all we need is to compute this numerator, which is very simply can be computed as selecting X item from the total part of successes in the population and selecting the number of failure, which is n minus X, from the total number of failure in the population, divided by n choose n. Keep in mind that X take values from 0, 1, 2, up to n, and here this domain is very similar to the domain of the binomial distribution, but with a certain or a particular condition that X can never be exceeds the R, because X represents the number of successes, and we have the total number of successes in the population is R. Similarly, the number of failure can never exceeds the capital N minus R, which is the number of failures in the population. So this is the number of failure in the sample. This is the number of failure in the sample, can never be exceed the number of failure in the population. Similarly, the number of successes in the sample can never exceed the number of successes in the population. So this represents the probability mass function of a hypergeometric distribution, and we summarize that X follows the hypergeometric. We write this as follows. We can abbreviate that X belongs to the hypergeometric distribution. The hypergeometric distribution we write it like this: we hypergeometric distribution with three parameters: the capital N, the small n, which is a sample size, and the probability of successes. I'm sorry. The three parameters are the capital N, which is the population size, and the small n is the sample size, and the number of successes in the population, which is small r. So you write it like this. So now let's summarize all properties of the hypergeometric distribution. Here is the probability mass function as we detect on the board, and then we can detect the number of expected value. By the way, we can explain this: n times r divided by n. If you move to the board, the expectation or the expected value of X is given by R times R divided by N. I'm sorry, this is N. So this is the number of the sample size, right? And this considered as the probability of success, right? Because we have total number of successes R in the population divided by the total number of the population, which is N. So this is very similar to n times b in the binomial distribution. Again, so this can be very easy to be memorized. Similarly, we can detect that the variance can be given by this formula, which is here again n times probability of success, and here this can be considered as the probability of failure, which is the number of failure n capital minus r divided by n capital. So this is the number of failure, and then at the end or the finally we multiply this component by a factor which is n minus n divided n minus 1. So this is by this fraction we can differentiate between the formula of the variance of the hypergeometric and the binomial distribution. And here we can discuss some examples of hypergeometric distribution. The first example is if we have a box containing n capital N marbles. Of these marbles we have small r are red. Suppose that n marbles are drawn randomly from the box without replacement, and x defined to be the number of red marbles. By this way, x belongs to the hypergeometric distribution with the capital N, small n, and small r. Another example, if we have 5 cards are choosing from a well-shuffled deck without replacement. So here we have 5 cards, denote 2, the n, small n equal 5, and let's x define as the number of diamonds selected. So we can compute the total number of successes in the population and the total number of diamonds in the deck, which are 13. So r equal 13. And n capital is the total number of cards in the deck, which is I think 56. So x will belongs to hypergeometric distribution with n capital equal 56 and small n equal 5 and r equal 13. Now move to solving. Before we going to discussing some exercises on hypergeometric probability distribution, it is very important to summarize some important notes. First, the F capital prime, which denotes to the characteristic of failure, might be any other characteristic than the one of interest. So the population may be divided into many characteristics, not merely to be true, which is very clear. Move to the next note. The hypergeometric distribution does involve dependence because the sampling is done without replacement. So this is considered as a difference between the binomial distribution. The other notes is the hypergeometric probability distribution enable us to find the probability of selecting x successes in the sample of n trials from total of n capital items in the population. Again, the population is of a finite number, so n has to be finite. Now move to solving example number 10. We assume that we have an industrial product is shipped in lots of 20, so we are shipping a lot of 20 items, and from each lot we are selecting a sample of f of 5 items. So we have n capital equal 20 and small n equal 5 is selected from each lot, and the lot is rejected if more than one defective is observed. And if a lot contains 4 defectives, what is the probability that it will be rejected? Find the expected number, expected value, and the variance of the number of defected items. Summarizing the information here in this exercise, we have example number. Number 10. Here we have n is defined to be 20, small n is defined to be 5, and the number of successes, which is the number of defectives in the sample, which is 4. And we are interested to find the probability of rejecting the lot. We know that the lot is rejected if number of defectives exceeds greater than or equal 1, right? So we are interesting if we define a random variable y as the number of defective items in the sample, then probability of rejecting will be equivalent to the probability of rejecting will be similar to the probability that y is greater than or equal 1, which is 1 minus probability that or it is very similar to b probability that y equal 1 plus probability that y equal 2 plus probability that y equal 3 and probability that y equal 4, because we know that the total number of defective can never be exceeding 4. So this is a total number of, so which is, I think it is easier to find it as 1 minus probability that y equal 0 using the complement rule. So all what we need is to substitute in the probability mass function of the hypergeometric distribution with y equal 0 and find this probability and then subtract it from 1. So we can say that y follows the hypergeometric distribution with n equal 20 and a small sample of n equal 5 and r equal 4. All what we need is to substitute in the probability of probability that y greater than or equal 1, which is represent the rejecting the lot, given by 1 minus, and then we'll substitute from 20, choose 5, and from the whole total number of successes we'll choose 0, and the total sample will be selecting from the successive, which is 16, selecting all the 5 from the 16. The final answer is given in the exercise. At the last, we need to find expected value of y. By the way, I represent in the answer in the slide the other way of answering. So this is another way, which is, I think, is short than the other that represented in the presentation. And then we'll substitute in the rule of n times r divided n to find the expectation, which is 5 times 4 divided 20. And the variance of y is given by n times r divided r and n capital minus r divided n times n minus r divided n minus small n divided n minus 1. All what we need is just to substitute in this formula. Again, the final answer is given in the slides. I think so far we finished discussing the hypergeometric distribution. We only have one extra exercise, and the final answer is attached to the slides. Probability distribution. This will be the final distribution that we discussed in this chapter. Poisson probability distribution. If we try to discuss the properties under this kind of distribution, we restrict this kind of distribution to the experiment that result in counting the number of times a particular event occur at a given time. Yani here we are assuming that we have a certain interval of time, and we are interested in counting the number of occurrences of an event over this time. Here we'll define a random variable, which is the number of occurrences of some event in a given continuous interval to be counted. So this will be our random variable. Then we have a Poisson process with parameter lambda greater than 0. We have some conditions under this kind of distribution. First, the number of occurrences is non-overlapping intervals are independent. It's very important that if we have more than one occurrences over these intervals of time, the intervals should be independent or not overlapping. So the conditions of independence here is very important. The next condition is the probability of exactly one occurrence is sufficiently short subintervals of length h is approximately lambda h. Okay, so here we have a fixed length of time, and this fixed length is h. So if we have lambda or the occurrence of the event is done with a mean rate lambda per unit of time, so if we have a time of length h, so the occurrence will be computed as lambda times h. Again, the probability of two or more occurrences is sufficiently short subintervals is essentially equal to 0. Recall that Maclaurin series expansion of the exponential function, which is e to the power lambda, which is given by this expansion, which is an infinite series, is important to prove most properties of Poisson probability distribution. So we use this formula to compute any property related to this kind of distribution, such as computing the expectation or the variance or any kind of probability. If x is a Poisson random variable, it's said to be x belongs to P for Poisson of parameter lambda. Again, this I think here in this notes or this final note will just give more explanation to the second condition here in B. If the event is an approximate Poisson process occur at mean rate of lambda per unit per unit of time, then the expected number of occurrences in an interval of length t will be given or computed as lambda times t. If you try to summarize the characteristic of Poisson random variable, this will be the probability mass function given by this formula, the expected value and the variance equal to the parameter of the distribution lambda, and the moment genetic function is given by this formula. If we try to detect or to discuss some examples of a Poisson random variable, first the number of cell phone calls passing through a relay tower between 9 to 10 a.m. is considered as a Poisson distribution. The number of flows in 100 feet of wire is considered as a Poisson distribution, and the number of customers that arrive at a ticket window or between 12 noon and 2 p.m. I think this line belongs to the previous one. The number of defects in 100 foot roll of aluminium screen that is 2 feet wide. All these examples belongs to the experiment of Poisson random distribution. Discussing some examples. Here we define a momentary function of y to be represented by this form, and we need to find this probability and the expectation and the variance. If we try to make a correspondence between this formula of momentary function and the previous one, we'll find a similarity to the formula of the momentary genetic function of the Poisson probability distribution with lambda equal to 3. So we can consider this random variable as a Poisson of parameter lambda equal 3. So the probability mass function is computed by this formula, and this represents all possible values of y. And if we try to compute probability that y less than or equal to, this can be simply done by summing all probabilities that y may take from 0 up to 2, which is the summation of the probability of y equal 0, y equal 1, plus y equal 2, and each of these probability statements will be computed using this formula. So all what we need in each time is to compute or to substitute in this formula by the value of y. So here we'll substitute with y equals 0, and then here we'll substitute with y equal 1, and here we'll substitute with y equal 2. At the end we'll find that the probability equal to 0.423. The expectation and the variance equal to each other and equal to the lambda, which is 3. Next to the example number 12. We have a customer arrive at a checkout counter in a department store according to a Poisson distribution at an average of 7 per hour. During a given hour, what is the probability that? So our lambda here is defined as the mean rate of the occurrence of the event per unit of time. So here we have a 7 per hour. So lambda will be equal to 7. Number A, no more than 3 customers arrive, so we need to find the probability that y less than or equal 3. So first we need to write the formula of the distribution that y belongs to Poisson with lambda equals 7, and then we'll substitute in the probability mass function with lambda equals 7 for any kind of possible values of y that takes it from 0 to up to infinity. Number A will be computed as the probability that y doesn't exceed 3, which is probability that y less than or equal 3, which is the summation of all possible values that may y take from 0 up to 3, which is the summation of y equals 0 plus probability that y equal 1 plus probability that y equal 2 and plus y equal 3. And each of those will be computed by substituting in the formula of the probability mass function by the corresponding value of y, like this, and at the end we will get this probability with 0.082. Now move to number B, which is at least 2 customers arrive. At least means 2 means 2 or more. So number B is simply computing the probability that y is greater than or equal to, which is computed easily by the complement, which is 1 minus probability that y is less than or equal 1, which is 1 minus probability that y equals 0 plus probability that y equal 1, and for each of those will be computed by substituting in the formula of the probability mass function of the Poisson distribution. At the end we'll get this value. Number C, exactly 5 customers arrive, so this means we need to find the probability that y equal 5, which is given by directly substituting by y equal 5 in the probability mass function of Poisson by y equal 5. At the end we'll get C as 0.128. And now we have some exercises, and as you can see, obviously I add the final answer to those exercises. By now, or so far, we finish this chapter. We covered all the important or the well-known discrete probability distribution, and now we will then meet in the next lecture to discuss the continuous random variable and its properties. I wish it's very clear, and if you have any question, please contact me via email or Moodle, and I will answer all of your questions.